So, when it comes to bonding and chemical reactions, it's really important for us to get into some of the overall. Thermodynamics is what we're actually focusing a lot on, and just generally energy. A lot of times when you talk about chemical reactions, you're talking more from a very holistic and kinematic side of things, meaning that you're just seeing how things are falling apart and putting together. What we're going to be focusing on is a lot more of the energy side of things. So I feel like what we're doing is taking a bigger step. The learning goal will be about energy, and we want to see the different types of chemical reactions, especially in regards of that. So this should be review, but if it's not, make sure to commit this to memory. You need to know what a chemical reaction is. And this is where you're talking about atoms, molecules, rearranging and forming substances. We actually covered this in Unit 1, but make sure you recommit this to memory. This is back again to the law of conservation. You shouldn't be surprised if I ask you a question about it again. It's going to be asking whether or not um, you are finding the substance in the products or the reactants. We will definitely be using those chemical equations again. Now, a key point that we didn't talk about before is that this rearrangement of atoms means that there are new bonds being formed. Sometimes it's just you cause a new bond, sometimes you destroy the bonds, and sometimes it's just them switching partners, okay? In the case of a general rule, it's not always the case, but as a it's like most of the time, it's because electrons find a way to get lower energy. One way to think about it is that they're anxious, they're very hyper all the time, and after they bond, they are relaxed and they're feeling safe. As a general rule, think about this for almost all nature. We note that this general law says anything that's too high energy is not a great state to be in. Most of nature prefers to be more calm, stable, and without needs to have chaos or randomness. They prefer to make sure everything is just nice and dandy. So, as a very general rule, when we cause new bonds to form, we're adding energy to this. Okay. This is going to be a concept you need to start working on because, as a very general rule, you represent this through a concept called Gibbs free energy. It is written as delta G, and the units for this is joules per mole. Lucky for us, we are not going to worry about the unit. You just need to memorize. It's something called joules per mole. This will be brand new. A lot of you guys have never heard of joules, and a lot of you guys will have never heard of a mole. But the way to think about it is that joules is a measurement of energy. So how much energy do you get per, and then mole is a measurement of how much stuff you have. Okay. In the future, you'll learn about this in chemistry. A mole is like a dozen. So it's a useful way to measure a number of things. It just literally means a number of things. So like if you're like, how much energy do I get per dozen is a way to think about that. And that's delta G. In the meantime, we're not going to quiz you on what joules per mole means, but we are going to ask that you recognize what the units are, okay? Delta G, again, is just change in G, which stands for Gibbs free energy, and that's what this symbol means. Start getting used to it. We are going to start throwing it around a lot, and we do expect you to recognize delta G. So we're going to cover 6 reactions. These are you're going to have to memorize. But more difficult than just memorizing them is you're going to have to understand how to recognize them when we show you an equation. So from now on, when you see an equation, you're not just going to see the chemicals and the formulas that make them, you're going to see the energy that shows up. There was a piece missing when we talked about photosynthesis and cellular respiration, and now we're going to start seeing it because this is important. For us, life isn't just about rearranging atoms. It's about how do you get energy so that you can even have a life. So, the first one is going to be called an exergonic reaction. This is a release of energy. Again, in this case, we're going to say delta G is negative. You're going to have to memorize these. In the future, once you get used to this, releasing energy naturally to you will mean that delta G is negative. So, one way to remember this is that it's exergonic. So, there's a G involved in there, the gonic part, and the X is that you're thinking like it's releasing, like X cross out the G, it's negative, it's going away. So, in general, when we say delta G is negative, these are all related. If you say it's releasing energy, you automatically also mean it's negative delta G. And if it's negative delta G or it's releasing energy, it's what we call a spontaneous reaction, meaning these will happen by themselves. They don't need you to add any ingredients, they don't need you to add energy, they don't need a boost, they don't need a catalyst. None of that is required. They should be able to happen on their own. You should naturally see it happening in real life. So, as an example, burning methane releases a lot of energy. This is again releasing energy. It is now an exergonic reaction, which means delta G is negative, which means it should happen on its own. These are all, if you want to, you can write them in your notes as equal signs to each other. Exergonic equals release equals delta G is negative equals they're spontaneous. Now, just as a quick note, Gibbs free energy means if you see that there's a lot coming out, remember G is negative, meaning there's a lot of Gibbs free energy in the product side. So the product side is where you're gonna see this, and it comes out in the form of light, literally shining light, or a glow, or a burst of light, not a burst of light, I wasn't trying to get at, radiating light. Anyway, there's also mechanical energy, meaning something pushes away or explodes or fires off, right? It's also heat and also electricity. There's also other kinds of energy, but just for our in terms of purposes, we're just giving those examples for now. Now, earlier we said we were going to cover six. The lucky thing is that it's actually three pairs, which means you really only have to memorize three because all of them have now an opposite partner. So instead of exergonic, you now have endergonic reaction. So again, now it's N, sounds like you're going in with a G. You must add in energy, so delta G is positive. Remember, everything was literally the opposite. Instead of releasing energy, you're now adding in energy, and delta G is now positive instead of negative, and it's not spontaneous. These things are hard to get to happen. You have to find some way to trigger them. So, Gibbs free energy is now on the left side. It is now part of the reactant side. And you'll notice here it's CO2 and H2O. That should trigger your memories, and you remember that especially on the product side, you now have C6H12O6 and O2. This is photosynthesis. They had to have energy on the left side. Once added in, we don't see it on the right side because it's inside of the molecules. Just like before, it's kind of hidden inside of the molecules and then suddenly it gets released. On the opposite now, we have energy on the left side, on the reactant side, adding into the reaction and becoming a part of glucose. So this is a common way of making sure that this reaction happens is to add heat. So a lot of times when you heat something up and it explodes or it starts reacting, this is why. It's because you literally gave it the energy to start the reaction. And now we have the energy diagram. This one you will see a lot more, both in chemistry as well as AP Bio. It is extremely important to understand this concept. And so this is where, even though you're not really learning anything in particular to as a new concept, it is important that you're able to analyze what's going on in the graph. Consider this a skill. It's not really, I would say, like it's half a skill. Most of you know how to read graphs. It's just how to understand this particular graph. On the x-axis, get used to this. A lot of science doesn't try to specify how much time exactly, just that there is some kind of progress going on. So if you have a reaction, you start with reactants and you end with products. This is obvious, right? We don't know how much time. Sometimes it's mere seconds, sometimes it takes hours, sometimes it takes whole years or even centuries or millennia, right? It doesn't matter to us. It just matters that the reaction is happening. Now, on the y-axis is how much Gibbs free energy. Don't be too confused. We're using Gibbs free energy specifically, but for all intents and purposes, for your conceptual understanding, treat it like it's just how much energy is there in that system. So if we're looking at a bunch of molecules, how much energy is inside of them? So if you're intimidated by this graph, don't be. It becomes quite interesting, or it makes a lot more sense once you start going from left to right. Ignore the yellow and the red for now. Just look at where the reactants are. In terms of energy, it's a little bit on the higher side, right? So you're going to start, and remember, you have to somehow release energy in order for it to become products, because we're saying this is for exergonic reaction. And by now, you should be memorizing what's endergonic versus exergonic, right? Exit, leaving, versus entering. So you have reactants, and it ends up being down here. If it released energy, it doesn't have as much energy as it's used to have. It will, in fact, become a lower energy product. So this yellow line then shows you, if you measure this, there is a difference in energy of reactants and products. And this energy is how much you will gain. You can actually absorb that energy and use it. In the case of our bodies, exergonic reactions would be like us burning through glucose and fats and getting that energy so that we can start running, literally moving our muscles or thinking, right? So there is, however, and this now you're going to have to memorize. It's a brand new word. This, you realize there's a bit of a hump first, a rise in energy before it goes on to products. This is because this reaction cannot happen just literally by itself. It often needs something called an activation energy. This is marked for you in red. Basically, if you draw a line across and you measure how high this peak gets, that's the energy you would need to get it to go. The best analogy and my favorite one, and it's the most common one, very frankly, is you literally just look at this as if it was a hill. If you're trying to get over down to where the products are, you can't do that without first biking up the hill or walking up that hill or running up that hill, whatever you want, an analogy, doesn't matter. But you first have to use the energy before you get to the top, and then, especially with the bike analogy, you just let gravity take over and then you just roll down, right? But before that, you had to force yourself to go up there. That energy is what we call the activation energy. This is why, for example, as with the example of methane, you can't just have methane gas and then it'll just suddenly explode by itself. It's not going to happen. You do need to introduce some kind of energy. And for it, it is volatile enough that just introducing a flame will cause that energy to spike, giving it just some energy to then burn and become the products that we see. So try this on for size. This is a problem we could present to you because this should be very easy for you to pick up and understand now what we mean by everything once you apply an actual problem. So if I give you a graph looking like this is now potential tier 2 or an FRQ question, we'll tell you, hey, the total amount of energy that's found in the reactant, we're going to measure it for you and tell you it's 75 joules per mole. Now, you should already see that unit and go, ah, gives free energy. If you don't, you can already notice that on the y-axis, we're saying gives free energy, okay? Sometimes I might get lazy and forget to write that, but it should be very obvious what it is as soon as I include that it's 75 joules per mole. Now, suddenly this goes up and goes back down, and its product energy is now a total of 50 joules per mole. Two things you can get out of this as a result of just me showing you that information. In fact, I don't even need to show you the graph. I can literally write this inside of a paragraph, and you should be able to say, well, then the activation energy needed would be however that much is on top minus the 75. So if this goes up to 100, you would say, oh, 100 minus 75 is 25, right? Let's make this different, though. Let's say it's just 80. So you say 80 minus 75 becomes 5 joules per mole. That's the activation energy. But then I say, well, how much energy gets released, right? First of all, you just by looking at this graph, you would say it's negative G, meaning there is product energy minus reactant energy, and you measure that out, and you say, now I lost energy out of my molecules. I lost a total of how much? 25. And since you should all know algebra by now, 50 minus 75 should be negative 25. None of you should be saying 25. This I don't consider a trick, because if it's positive 25, it means you gain energy. So as your choices, you might see positive 25 versus negative 25. At this point, it's not trying to be tricky with you. The signs really matter. When your math teachers metaphorically slap your wrist and tell you stop messing around with the negative signs, you need to make sure they're in the correct places. This is why. It means a completely different direction when you have positive versus negative. So it will not be a wrong answer. Well, sorry, a wrong answer, a bad selection for me to put in the positive or negative version of what delta G should be. You should be the one who's responsible for knowing whether it's negative or positive. It's a very big difference. It makes a difference between an endergonic reaction versus, in this case, an exergonic reaction. So, if we show you a graph that looks like this instead, now keep in mind, this is what you're looking for. If you're looking at reactants being lower, products being higher, you now have to add energy into the chemicals in order for them to become higher energy. So, as mentioned before, this is all essentially just the opposites. Reactants now lower, products higher. The energy added should be an increase. It should go higher. Remember, if the arrow points up, that means that's the positive direction. If you go down, it's negative direction. In the case of reaction progress, right is positive, left is negative. Now, reactants going up, this is now the activation energy, but the activation energy needs to be measured from the top of this peak to where the reactants are, not to where the products. Some of you might accidentally draw that down and say, oh, well, that's the activation energy. If I ask you to calculate this, you have to make sure you transition state peak all the way down to the reactants. Don't forget that's the rule. Now, endothermic and exothermic is a general term. There is now a more specific term we're going to get into, and it's exothermic. If you hear about like anything thermal wear, or whatever else, you're talking about some kind of heat. Either you retain heat or you get rid of the heat. Generally speaking, though, it just means heat. Okay, so exothermic, again, you're exiting the therm, which is now heat. The heat is now negative. This is specific because when we're very interested in only heat, we're talking about thermodynamics. In reality, there's a lot of energy that gets released in all kinds of ways. As we mentioned before, when we're talking about exothermic and endothermic, there's light, there's, literally something gets pushed away if there was a force of air coming out. There's a lot of things that happen. However, for all intents and purposes, exo and endothermic reactions are very important because heat oftentimes is the way you tell whether something is working in terms of life. A lot of times when we're talking about calories, it ends up becoming purely a measurement of endo and exothermic reactions. So we're not going to cover into super detail where these are applied. We're just going to loosely apply them to things like photosynthesis, and we're going to represent heat energy here as enthalpy and delta H. The reason we're just going to kind of skim over this right now is because a lot of you guys, once this gets into AP Bio as well as, say, AP Chem, you might start getting confused and going, wait, what is it? I thought this was this. I thought that was that. Just for now, this is why, again, we're presenting it the way we are. Delta G is general, like overall, how much energy do we have? But enthalpy, the term of enthalpy, delta H, is now, and if you want, delta H makes sense because it represents heat, is specifically about how much heat energy there is. Okay, so there could be more energy in the form of other types of energy, but we're only interested in the heat, so now it's enthalpy. All right, so the opposite is endothermic reaction. You're putting thermal energy into the chemicals, into the reactants. So it's on the left side of the equation, it's positive heat. The enthalpy is delta H again, is now a positive number. And we measure in kilojoules per mole as a default, but don't get that confused. Kilo is just 1,000 joules instead of regular joules, okay? So here's where the curveball comes in. You have the last two reaction types. Now, before we talked about this two, we had exergonic, endergonic, exothermic, and endothermic. Effectively, the exact same thing. Those are actually pretty easy to memorize because, for the most part, same concept. The difference being simply in what kind of energy we're talking about. Gibbs free energy is G, general, and thermic energy is H, heat. Okay, so we're just talking about those two differences. However, here now we have a new concept. We have catabolic versus anabolic. For catabolic, you have polymers becoming monomers and energy. It doesn't have to be specifically polymer and monomer, by the way. In reality, catabolic talks about larger, more general terms. Like it breaks down some bigger complex molecules into smaller ones. Sometimes it's as simple as, oh, I took a piece of that molecule off, and that's all I'm doing. And that's enough for it to count as catabolic. It doesn't have to be a large polymer becoming tiny chunks, but for all intents and purposes, since we are talking about this right after talking about biomolecules, we are talking when a polymer becomes monomers, you now have a release of energy. So this tends to release energy. Again, this is a very general term. For all intents and purposes, you can memorize it this way and it will work. Keep in mind, since we say it tends, in the FRQs, we will probably come up with reactions that show you the opposite, where now you're like, is it catabolic or is it anabolic? The most important aspect of catabolic is that it breaks down from bigger to smaller molecules. There's now more pieces than you started off with. Okay, so hydrolysis, this is where you link it up. And since it tends to release energy, you're going to be describing it also as, is it exergonic, endergonic, or the thermal ones. So anabolic then is the opposite. You have smaller pieces and you end up with less pieces than you started with because you were adding them up together. In order to do that, you have to have energy to force them to stick together. So again, the most important aspect of anabolic is that you're making a bigger and more complex molecule, not just necessarily monomer to polymer, but anything that's just bigger pieces. Once you have smaller ones starting and then you make them into bigger ones, that's anabolic. And again, in general, you tend to need energy to feed into it. So this is where we talk about dehydration. I will again be referencing in a more general term of condensation, but this is where we now start tying this into biomolecules and how this can become very difficult. I can give you a simple equation and ask you, especially if I show you the energy here, a lot of questions. I can be asking you, is it catabolic or anabolic? Is it exothermic or endothermic? Is it exergonic or endergonic? Is it a hydrolysis or dehydration slash condensation? Is it what type of biomolecule am I talking about? And so this is where it gets incredibly detailed, and why I'm saying this is more of a conceptual thing. You have to be able to relate those facts to each other and analyze and understand what you're seeing. Memorize the rules, memorize all 6 of these definitions, and then when you're thrown problems, you should be able to analyze them, especially with that graph. So as a practice problem, look at this information. This is how we'll be presenting problems to you. We'll tell you, for example, N2 plus 3H2 becomes 2NH3, and the delta G is negative 100 kilojoules per mole. The second problem is CH4 plus 2OH becomes CO2 plus 2H2O, and the delta G there is negative 200 kilojoules, and the delta H there is negative 74. So for all 6 reactions types that we talked about, what would they be for each of the problems? For problem 1, problem 2. Take a minute. We're going to go and do a quick countdown, and we're going to tell you the answers. 3, 2, 1. For the first reaction, it is an anabolic reaction because you had 2 pieces adding up to become 1. So you built a more complex molecule. For exergonic, you're talking about a reaction of delta G is negative. Therefore, you lost energy, you released energy. It is now exergonic, okay? We can't consider whether it's endo or exo because you did not get evidence of it for delta H. We know energy was released, but it might not have been heat, so we can't say anything about it. For the second reaction, we did in fact give you delta H. So it's exergonic because its delta G is negative, and it's exothermic because its delta H is also negative. Now, it may be a catabolic reaction, but in this case, you guys don't have enough information, and so we're not going to force you to answer that one. This is the kind of examples where you have to analyze and go, well, does it fit the rules? So now that you've had a sample, let's try another one. Let's look at the top one. You have that reaction on top here, and he did very specifically show you a connection here. We're going to try to make sure you guys see that, because this is very important that you guys know what we're trying to hint at here. There's not a random dot dash there for no reason. And we also provided delta G and delta H. So now there's a lot of information you can look at, and you should be able to, once again, decide for all 6 reaction types, which ones are they. So now you can do all 6. But remember, you can't actually choose 6 to say, oh, it's all of them. They're 6 pairs. So you really should end up with only with 3 answers. They just might be opposites of each other. In this case, we literally gave you the exact equation. Well, not exactly equation, but pretty close. They're just opposites of each other. In the first one, it's anabolic. Again, you have 2 smaller pieces added up, becomes I don't know, anabolic. Ana sounds like you're adding up, and so it becomes you're adding them into a larger piece. And then you have endergonic reaction because it's positive kilojoules. Same with endothermic reaction because it's positive delta H. So with this one, it's the opposite. Catabolic, you have a larger piece, that bond gets broken, and now it's smaller pieces. And exergonic reaction is you release the energy. It's going to be on this side because it's negative delta G. Exothermic is negative delta H. There you go. Pretty straightforward.